Heat flow. Heat is essentially microscopic kinetic energy. As you heat an object up, the molecules or atoms in that object move, vibrate, rotate with greater amplitude and greater velocity. So how does this kinetic energy get transported from one part to another? In conduction, the medium itself, this metal bar, does not move, but the heat is transferred through it. In convection, the heat is transported with the movement of the fluid, and in radiation, the heat is transmitted from the sun to the earth, in this case, through a vacuum, without any medium whatsoever, via electromagnetic waves. So as you heat an object, its temperature increases. The amount of heat is a change in energy of that object, is going to be proportional to that change in temperature. It's also proportional to the amount of mass that you're trying to heat up. Certainly, if you want to heat something that's twice as heavy, you're going to need twice as much energy. If you want to heat something by twice as much change in temperature, you're going to need twice as much energy. To make an inequality, we add C, the specific heat. This is how hard it is to heat up this particular substance, or the amount of energy that you have to give a certain amount of this substance to raise it a certain temperature. We define a calorie as the energy needed to raise 1 gram of water 1 degree Celsius. So therefore, the specific heat of water is 1 calorie for every gram degree Celsius. Joule did the famous experiment where he was able to measure the increase in thermal energy in calories that resulted from losing a certain amount of physical energy in joules. It turned out that 4.2 joules of mechanical energy resulted in a gain of 1 calorie. So the specific heat of water can also be represented as 4.2 joules for every gram degree Celsius. We can compare the specific heat of water with many other substances. These units are joules per kilogram degree Celsius, so everything's larger by a factor of 1,000. So here's water at 4,200 joules per gram degree Celsius. When we compare this to other substances, water has a much higher specific heat than anything else except hydrogen. Okay, hydrogen is very light, and so therefore it has a very high specific heat. But how are you going to hold kilograms of hydrogen? One of the takeaways from this is if you want to store thermal energy, water is a very good means to do it, as long as you don't have to have the temperature at greater than 100 degrees Celsius where water boils. In particular, we can compare it to some metals that have a smaller specific heat by a factor of 10 or more. So let's talk about conduction. In a solid material, you can add heat to one part of it, and the heat, the kinetic energy, is transmitted by means of bumping and vibrating into its neighbors. This is a very slow process. However, it can be greatly accelerated if we have free electrons. So in a case where we have metals, you may have learned that metals are positively charged ions in a sea of freely moving electrons. And so if you heat one part of it, the electrons carry that kinetic energy very fast to other parts of the object. And that's why metals have a very high conductivity. How do we define heat flows through materials? P is the power or the rate of energy transport through this substance. And we want to know what determines how quickly energy will go through that substance. If we represent this as a cylinder and the heat flows from the hotter side to the lower side, we can see that a certain amount of heat will flow through here, a certain flow of energy. And if we have another one, we'll have twice as much energy. The rate of thermal transport is proportional to the amount of tubes, and therefore the amount of area we have available to carry the heat from one side to the other. The rate of thermal transport is also proportional to the difference in temperature from one side of the material to the other. And it's also inversely proportional to the length. If we make the distance the heat has to transport through twice as wide or twice as long, we can see that for the same distance, we only have half the difference in temperature. And so the distance that the heat has to travel across is in the denominator. And what we have here is what's called the thermal gradient, the rate of temperature difference. So degrees Celsius per meter in the material. So as you increase the temperature gradient, you're going to increase the rate of thermal transport. And we note thick insulation works better than thin insulation. So what is K? Thermal conductivity of the material is how easily it transports the heat energy. The units are watts of heat transported times the distance you have to transport it across per Kelvin of temperature difference per meter squared of area that you're transporting it through. And when we cancel these units out, we have watts per Kelvin per meter are the units of the conductivity. We can look at the thermal conductivities of a number of materials and see there's a huge difference, a factor of 40,000 between copper of 385 and styrofoam of 100. This means if you had a piece of copper that was a perfect cube of a meter across, and you had a difference in temperature from one side to the other of 1 degree Kelvin, there'd be a heat flow. That heat flow would be 385 watts, where if it were styrofoam, the heat flow would only be about 1/100th of a watt, or 10 milliwatts. So you can see, yes, styrofoam is a really good insulator, and copper is a really good conductor. Here's another way to represent the conductivities in graphical form, and we can see a huge disparity for air, which is a really good insulator, as long as you don't let it convect, all the way to copper, and we have lead, sandstone, glass, concrete, soil in the middle there. So in convection, you have a hot point and a cold point, and you don't just conduct the heat across because the heat can move with the flow in the medium. As the medium gets hot, its density decreases and it rises and comes closer to the cold part where it gets colder and drops back down. This is much more effective at moving heat because the hot substance comes right up next to the cold part, and so the distance that you have to transport or conduct the heat across is very, very small. This is something that we notice whenever we cook beans, let's say. If you have water boiling, you know that the water is going to be pretty much a uniform temperature everywhere, that the heat is being transported from the bottom to the top really well. And let's say your beans get thick enough to stop that convection. You know what's going to happen. You're going to burn the hell out of your beans on the bottom, and the top of the beans are going to cool off because now you can only conduct the heat if you can't convect it. Here's one very important convection cycle that causes our weather. Imagine in the daytime, the land heats up much faster than the water. Why? Oh, because water has a very high specific heat, and its temperature doesn't change through the day very much at all. And the land gets hot really fast, so the air rises and convects, and we get what's called an onshore breeze, and you surfers hate it. But at nighttime, the land cools down faster, and the water stays the same temperature. So now the air is rising over the water and dropping over the air, and you have an offshore breeze, which is why surfers like to get out early in the morning, because the wind is blowing toward the water. Radiation is the transport of energy by means of light. So when we think of light, we usually think of the visible light that we can see, the Roy G. Biv colors. However, visible light is just a small portion of the spectrum of electromagnetic waves. There also exist waves of much longer wavelength, such as infrared, microwave, and radio waves, and shorter wavelengths, such as ultraviolet, X-ray, and shorter yet, gamma rays, which are on the order of the size of a nucleus. As we go in the direction of shorter wavelengths, we get much higher frequencies. Additionally, in this direction of shorter wavelengths and higher frequencies, we have higher energy. Gamma rays and X-rays can go right through you, ultraviolet rays can only damage your skin, and infrared can only warm you up. Down here we see the temperature at which we might glow in these different wavelengths. What do we mean by this? If we take a look right here, we can graph the intensity of light versus the wavelength. And here we have the Roy G. Biv colors again. Now I've turned it around so that this direction here is higher energy. And so this is the infrared on this side, and this is the ultraviolet on this side. So the intensity can be thought of as the power flux, or the amount of power we get per square meter, such as sunlight has a power flux of 1,000 watts per square meter when we're in strong sunlight. So what we see is as something is hot, it glows, and it glows in all wavelengths. But the greatest intensity is going to come at a certain wavelength that corresponds to the temperature. As the temperature gets higher, the wavelength that it peaks at is shorter or of higher energy. So when we look at the different temperatures, we see something interesting. As we get to higher and higher temperatures, the peak gets further to the left or for higher energies. And that we know. If something's hot, it might glow red. If something's really hot, it might glow white. And if something's really, really hot, it's going to glow blue and also emit like X-rays. And it just so happens that our sun is about 5,600 Kelvin, so it's going to peak right about here, and most of its radiation comes to us in what wavelength? In wavelengths that correspond to visible light. So for instance, what we know is we can see the sun because it's glowing, but I can't see you at 300 Kelvin because this is where you peak. However, we could see you if we looked at you with an infrared camera, which we'll do in a minute. The entire intensity of light emitted, that is the area under the entire curve of all wavelengths, is equal to the Stefan-Boltzmann's constant times temperature of that object to the fourth power. Think about that, fourth power. That means if you double the temperature, the intensity is going to go up by 2, 4, 8, 16 times. And so when things get really hot, their conduit of greatest heat loss is going to be in radiation. So what's Stefan-Boltzmann's constant? We can all remember that. It's as easy as 5678. 5.67 times 10 to the minus 8 watts per meter squared of area per Kelvin to the fourth power. Oh, emissivity. What about emissivity? Well, it turns out that rough black surfaces have an emissivity of 1. That means they emit as much as they can. But smooth silvery surfaces don't emit at all. Don't emit or don't radiate. So for instance, take a look at my friend Scott here, but look closely at this box. We have a silvery surface right here and a rough black surface here. This box is really hot. Now look at the infrared camera. Here you have my friend Scott, pretty warm. And here you see this box is all the same temperature, but this side is not emitting. This side is emitting a lot because it's black. This side is not emitting anything because it's silver. In fact, what you see is the cool reflection of light coming from over here and the little bit of reflection from this hot lamp right there. You see that little reflection. So what we see is we always knew that black surfaces absorb light, but it's also the case that black surfaces are going to emit light more when they're hot. So for instance, here's my house several years ago, and here it is today. You can see many things have changed. I cut down the big tree, and I painted it. But look at the roof. The roof used to be dark green, and now it's white. And so as a result, not only is my attic less hot in the summertime, but in the wintertime, I radiate away less heat at night, and so my house stays warmer. This is called a cool roof, and it's a very green technology. So emissivity is a coefficient of absorption and coefficient of emission. Our most important example of radiative transport, of course, is the sun. Right? The sun is really hot. It radiates, it peaks in the visible light. The earth is just warm, and so it peaks in the infrared, and most of our heat is lost into space through infrared radiation. And so this is the radiative energy balance that's so important for the earth, because all of the heat that comes in from the sun is radiated out into space. And we'll discuss this more when we talk about global climate change, how we're absorbing some of this infrared light through our carbon dioxide emissions. So what do we know? Heat is microscopic kinetic energy. In conduction, you have a solid medium, and the heat is transferred by atoms bumping into each other, although moving electrons greatly improve the rate of heat transfer. In convection, the heat is transported with a fluid medium. It works much better than conduction. And so insulation technologies are really about stopping the convection through means of like fiberglass or feathers or something like that. And in radiation, light energy travels without a medium at all, and higher temperatures correspond to higher frequencies